And let me introduce the next speaker to you. The next speaker, as you know, will also be your science reporting teacher. And Dr. Sitabhra Sinha. So this is what he has written himself, so I'm just going to read it out. Sitabhra Sinha likes to think of himself as a disciplined, fluid scientist. Formerly, he is a professor of physics and the dean of the Computational Biology graduate program at the Institute of Mathematical Sciences, Chennai, which is just across from us, you know that, next street. And was earlier also adjunct faculty of the National Institute of Advanced Studies in Bengaluru and the Department of Computer Science, IIT Kharagpur. He did his PhD on neural networks when it was not at all fashionable, and he did it at the Machine Intelligence Unit of the Indian Statistical Institute, Kolkata. Can I have some silence, please? Subsequently, Dr. Sinha did his postgraduate research at the Interface of Physics and Biology in the Department of Physics of the Indian Institute of Science, Bengaluru, and later mucked around as an American Heart Association postdoctoral fellow with clinicians and cardiac surgeons at the Weill Medical College of Cornell University, New York City. He joined the faculty of Indian Institute of Mathematical Sciences in 2002, and he holds joint appointments in the theoretical physics and computational biology groups of the Institute. He works on anything that looks exciting, spanning areas like systems biology, economics and social sciences, and computational linguistics. And he's got a provocative title called We Should All Be Physicists. Right, Sitabhra.
Thanks, Nalini, for this introduction. Always a pleasure. And Tarun's act is a hard one to follow, but he also made my job easier because I'll be using some of these analogies with intelligent machines in my talk. So, every now and then I will actually be alluding to some of the stuff that he's already talked about. Right, so as some of you might already guess, my title is a tongue-in-cheek allusion to Chimamanda Ngozi Adichie's book. And I'll try to, kind of live up to the title and try to convince you that, you're all physicists, whether you know it or not. Right, or you should strive to be one. Right, so I have divided my talk into kind of, chapters, like a Tarantino movie. And the first one is defining the creature. What's a physicist? Okay. Right. So when you hear the word physicist, what comes to your mind? Is it this? Right. So this is, the last couple of years, you have this image of this angst-ridden physicist racked by guilt, but nevertheless a creative genius. Okay. Preferably quoting Gita during, coitus, whatever. And if you go back earlier, if you are a movie buff, you'll realize that this movie, so this is one of the classics, Stanley Kubrick's Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. And now you have a very, very different image of a physicist, right? Evil, right? And so you have Peter Sellers playing the role of an ex-Nazi warmongering physicist, right? Who, if you have not seen the movie, I would recommend you to, by hook or by crook, see the movie as soon as you can. I mean, Peter Sellers does a fantastic, he actually plays multiple roles in this movie. Apart from Dr. Strangelove, he also plays a British Army officer who's guarding a particular nuclear base and other characters and so on. And so, but in his role as Dr. Strangelove, you'll see that very much like Darth Vader, he has a black gloved hand, and this hand essentially involuntarily tries to give the Heil Hitler salute at very inconvenient times. And he's always with his other hand trying to bring this down, right? And not very surprisingly, it's actually inspired by some real characters, some truly, slime balls, like Edward Taylor, often referred to in the American media as father of the hydrogen bomb, but I don't know how to frame him. I mean, he's a real low life, right? Read about him if you want, okay? And also a mix of Werner von Braun. He was Hitler's golden boy. He was the designer of the V2 bombs which rained on London during the Blitz. But of course, his role as a Nazi was completely forgotten after the war because the Americans kind of immediately spirited him over to the US and gave him the job of overseeing the design of their moon rockets. Okay, so suddenly you have this, whitewashing of his entire past, and he became the hero of the NASA's banned spaceflight program and so on. So it's the Doctor Strangelove is like a combo of these two characters, and you have this image of a physicist as a satanic figure, right? Also a very common trope in movies. And then, sort of my favorite, the goofball physicist, right? Genius, but complete social misfit, okay? So Christopher Lloyd plays a wonderful role as Doc Brown in Back to the Future. Again, hopefully some of you have seen this movie. Yeah? Okay. So this is the scene in which he rigs up this car, a DeLorean, as a time machine, right? And he puts his pet dog as a test experiment, right? And you have Marty, played by, I forget his name. So his dog is, of course, conveniently called Einstein, and then it hits a particular speed, and then boom, it travels into the future. Okay? And this is also a trope which is very, very commonly used in movies, to show a physicist, who doesn't care what happened to his dog as long as his experiment worked, right? So that's why I said mad, bad, dangerous. These are usually the terms you associate with physicists, okay? And things are not helped by the fact that one of the most famous physicists of the 20th century, most popular photograph on the net seems to be this, okay? All right. So what did this guy do? Sorry to break it to you, but this guy didn't do any of that. Shock, silence, awe. It's this guy, right? That guy was basically, just resting on his laurels. It was this regular looking guy. I mean, he's so regular, he could be a government clerk. Well, guess what? He was a clerk in the Swiss patent office when he discovered relativity. So from 1902 to 1909, he basically worked as a patent clerk at Bern, okay? And that's when all the famous work that he's known for was done, right? So by 1915, he had done effectively everything that he was famous for. And he was only 36 at that time, okay? After that, he didn't really, he continued to do physics, but not something, which was really significant. Even the Bose-Einstein condensate was primarily Chaten Bose's contribution. He was basically the guy who made it, palatable to others, okay? So physics is done not by, those cartoonish figures of evil or the lovable character like Doc and so on, but it's usually done by pretty regular folks. Okay. First lesson: right? Okay. Second chapter. Why should we be concerned about physics? And why not let physics to people who are specialized to study it? Because I would like to argue that long before data science became a thing, okay, physics basically was data science. It's in fact what I would call the data science. Okay, because what is physics but a way of having a conversation between observation and theory. Now, theory is a very loaded term. I know, like in humanities and social sciences, theory has a very particular meaning. Physicists also mean something very particular by theory. But I'd like to show to you what we mean by theory. Right? Okay. So, I would consider Miss Marple not so much as a detective, but actually as a data scientist. Okay? Agree? Okay, first of all, how many of you know Miss Marple? I realize that. Okay, not too many, right? Yeah. People always complain that I'm like actually a dinosaur. So Miss Marple is this character invented by Agatha Christie. Just as popular as Poirot, actually. In fact, I like Miss Marple more than Poirot. I find Poirot completely insufferable. Miss Marple lives in the village of St. Marymead, and she is an inveterate gossip. Okay? She basically knows everything that's going on in the village through her maid, through her friends, and she manages to solve crimes which completely befuddle the professional investigators, like the police. Okay? And in one of the books, Miss Marple explains her methods. Okay? And when I read this method, I thought, hold on a second. I mean, this is exactly what I do, or what typically a data scientist does. So what is it that she said? So she said, look, in a small village with nothing to distract one has ample opportunity for becoming what I might call proficient in one study. And what's that? One begins to class people quite definitely just as though they were birds or flowers, groups so and so, genus this, species that. Sometimes, of course, one makes mistakes, but less and less as time goes on. Now, let's go back to Tarun's lecture. Okay, Tarun didn't explicitly mention this, but if you look at machine learning, there is a particular routine where you first give the machine a lot of training examples. So you show them, like for example, if you wanted to distinguish between cats and dogs, you first show it lots of pictures of dogs and say, this is a dog, this is a dog, this is a dog, this is a cat. Okay? So you first have got to get the machine to know what are dogs and what are cats. You of course don't know what's going on inside the machine. You hope that it's being able to kind of distill this essence of what is a dog and what is a cat. So that's the training phase. Okay? And the way that it's essentially distilling this essence of a dogness or catness is what we call learning, or sometimes we call it function fitting. So what does a function fitting mean? So how to figure out whether to take out your umbrella when you go out on a particular morning? Anyone?
When it looks like it's about to rain.
How do you know it's going to rain?
Look at your weather app on your phone.
Oh, okay. Yeah, so you're, of course, you're a weather app generation. Yeah, no. Well, assume that there's no weather app, or your phone's on the blink.
Look at the sky.
Very good. So you look at the sky, and what makes you think it will rain?
If it's dark or cloudy.
Fantastic. And how do you know if it's darker and it's more cloudy, it's going to rain?
Because that's historically.
Absolutely. Yeah? So you use past experience. So what do? You said, cloudy. Did it rain yesterday? It did. So it's cloudy today and it rained yesterday. So we are in kind of a rainy season and it looks like it's going to rain. Let me take my umbrella. Okay? Other days, it looks perfectly fine, but it did rain yesterday and day before. And you get caught in a sudden downpour sometime in the late afternoon. So you say, new thing to learn, that even if it's sunny early in the morning, the fact that it rained the past few days should make me beware that I'm probably in the rainy season and weather might change in the afternoon and I should take my umbrella. What are these? These are, in some sense, your training data. Okay? So what you have is, in some large dimensional variable space, where the variables could correspond to, did it rain yesterday? Did it rain day before yesterday? Did it rain the day before that? Is it cloudy? Does it feel like it's kind of cool and so on? Lots of possible variables out there. And each of these variables essentially define one more dimension in space. So in this dimension, you're putting in points that when this is true, it's likely to rain. When this is true, it's not likely to rain. So basically, over this large dimensional space, you're putting in points which you say, okay, this in this part of the space essentially corresponds days, conditions in which it will rain, and this corresponds to days it will not rain. And so this boundary is what I call the function, the surface, okay, which is basically dividing conditions which will rain versus conditions which will lead to days which will not rain. And in your head, you're doing this all intuitively. You're not using any sophisticated mathematical model. You're not even aware of, that this is a cubic function or it's a sigmoidal function or whatever. Yeah, you do it all intuitively, but nevertheless, your brain is in fact doing some kind of a function fitting, or that's the way a learning theorist will tell you, right? Right. So Miss Marple is doing something similar. Okay, if this person has such and such and such character, likely that this person is going to do something very unpleasant. Okay, so she's doing a function fitting on the characteristics of individual human beings. Right. Next, you go to testing phase. And then to one taste oneself, it is so fascinating, to apply one's judgment and find that one is right. Okay, so what you're doing is, okay, so you have made this prediction, it will rain or it will not rain, and then you go out in the world and you test your prediction. So if you made a wrong call, you're going to get wet. You didn't carry your umbrella and it rained cats and dogs. Or, you took your heavy umbrella along with you and it didn't rain. Okay, so you could get yourself wrong, and then that's something you use to tweak now the function that you had fitted. Okay, so this is the testing phase in which you try to correct your function, and finally this results in a classification, the conditions under which it will, for example, rain or not rain, or the conditions under which a particular individual with a particular set of characteristics may commit a crime or may not commit a crime. So this is supervised classification, or as Marple puts it, in fact, the only way is to compare people with other people you have known or come across. You'd be surprised if you know how very few distinct types there are in all, right? So even though you might think that there is a infinite number of possible human characteristics, it is inherent in us to always try to classify it within a few types. Okay, that's just the way humans do it. I'm not saying that that's the truth or that's how nature works. By the very limited ability of our cognitive apparatus, we are bound to always try to classify an infinitude of possibilities into just a finite set of classes. And that's basically classification. Okay? So if you show a data scientist only this, that person is going to nod her head and say, yeah, this looks like data science. And then, but you don't show this and you only show this, what is this, right? So, my argument is, this is precisely what physics has been doing ever since Galileo Galilei, okay, invented the whole thing. Galileo is, in some sense, the first ever physicist. So what did he do? So one of the things he's very well known for is coming up with the pendulum clock. And how did this come about? So he was in the cathedral, probably at Pisa, and there was this huge lamp which was hanging from the ceiling, and it was kind of swaying in the wind, and sometimes, depending upon the wind, it would sway like this, and sometimes it would sway like this. And he was curious, what is the period, what is the time it takes for the lamp to complete one full swing? So it goes from here, comes back to its original position. And he was timing it with his pulse, there being no watches at that time. And much to his surprise, he realized that it doesn't matter whether it swings like this or whether it swings like this, it always takes the same amount of time for it to complete one full swing. He was fascinated and he said, okay, what exactly does this time period depend on? Now, this is where things become really interesting. It could have depended on so many things, right? It could have depended on the nature of the material the string is made of, the fact that it's a lamp and not a bob, or that the candles are lit versus they are not lit. They could have depended on so many things, right? Galileo systematically eliminated all possible complicating factors and realized it just depends on the length of the string from which it is suspended. Okay? So essentially the time period of the swing is just related to the square root of the length of the string. Okay? Forget about this gravitational constant for a moment, because at that time there was no way of calculating this, but you really don't need it, because what Galileo was really interested was, suppose I increase the length of the string by a factor of 4, so I make it 4 times longer. What will happen to the time period? So this expression will tell you that it will change by a factor of square root of 4, which is 2. So if you increase the length 4 times, the time period will become double of what it was originally. Okay? And he used this idea to create a mechanical clock, the pendulum clock, because he said, well, this is a fantastic way of having a very accurate instrument for keeping time. Because all I have to do is make sure that this length of the suspension from which this bob is hung is kept constant, and I have a clockwork mechanism which makes it swing, and then that's it, right? I mean, as long as this clockwork mechanism makes it keep swinging, my time period is fixed. So I can use this swinging motion of the pendulum to essentially keep very accurate record of the time elapsed. Okay? Now, what lesson do we take from here? The fact that if we have observations of 2 things, so in this particular case, in this particular case, time period of oscillation, length of the pendulum, and I can fit them using some simple curve, then I have managed to relate them using a function. Okay? And that's basically the relation between these 2 variables. And that's what, in some sense, physics or data science is all about. You're trying to see what's the relation between x and y. Going back to Miss Marple's example, if this person shows a particular propensity or a particular fault of character x, what's the probability that this person is going to commit a crime? Y. Okay? And that's what basically she's trying to, that function is what she's trying to fit using all this gossip that's coming to her. Okay? And then she's trying to make a prediction that, okay, if I observe this propensity in this person, the probability that this person is going to commit this crime is pretty high. Okay? Okay, that's data science in a nutshell for you. All right? But where does the problem come in if it's so simple? The problem is, of course, in the real world, you don't know what is X. Okay? For all you know, it could be hundreds of different variables, right? I mean, how did Galileo come to know that it just depends on length? It could have depended on so many different things. The material of which the bob is made of, okay? Which region of Earth is he observing? Or is the sun up or down the horizon? It could have depended on so many different things. He was lucky that he could reduce it to just one variable. Okay? Miss Marple is not so lucky, so she has to depend on maybe 2 or 3 variables. But again, you know, it's just a few variables. But when you come to things like trying to predict, you know, so if you are managing a wind farm, okay, you are faced with a real problem, right? You need to know, is there going to be enough wind tomorrow for me to produce this much megawattage of power, which I can supply to the Tamil Nadu power grid? Okay. Now, if I make a miscalculation and there's not that much power generated from my windmill, I've got to buy that much power from the market. And of course, if I buy power from the market when I need it, I'm going to pay a premium. Okay? So if I can manage to figure out beforehand, okay, I'm not going to be able to make that much power, so I better buy this 24 hours in advance, I get a discount because I'm buying it in advance. Right? But then suppose I made a mistake and it actually, I managed to generate surplus power. Then I've wasted money by buying power when I didn't need it. Okay? So if I make an underestimate or overestimate, in both cases, I'm actually facing a loss. Right? And so for me, it's very important that I be able to predict to, you know, high degree of accuracy how much power I'll be able to generate 24 hours in advance using my windmill. And the problem is, it's the power or the wind that is going to be generated 24 hours later is not a very simple function of just, you know, let's say how much wind is there now. It depends on so many different things, right? It could depend on temperature, humidity, and not just the location of my windmill. It could be dependent upon what's happening, let's say, in the Arabian Sea, or what's happening in the Indian Ocean, or maybe what's happening in Australia, right? Because the weather is a global system. And so it becomes a really difficult high-dimensional problem of trying to figure out all the possible variables which could be affecting how much wind would be there tomorrow at this time. Okay? And in essence, data science is all about, the problem of big data is all about, you know, you having to deal with tens, hundreds of millions of factors and trying to, you know, fit some kind of function over that to try to predict what's going to happen at a future time. So, in some sense, because we can't visualize millions of factors in our head, the traditional role of science had always been to try to reduce the number of factors that we need to see and make it a tractable problem. And this is where the role of human genius traditionally would come in, right? So all the big geniuses that we know would be able to do this. Galileo, for example, would reduce this just to a single variable. And then when people wanted to understand, like, can we predict solar eclipses? Okay? Again, it could have been affected by so many different things, right? I mean, every culture has a story about why solar eclipses happen, right? Either it's a demon which is swallowing the sun or whatever, but these are not predictive stories, okay? They're explanative stories, okay? If you want a predictive story, you got to do something more. You got to figure out what are all the variables which are relevant in trying to predict when the next eclipse is going to be, okay? And for this, people started observing the motions of the heavenly bodies, and this has been, of course, going on for a very long time. I mean, even the Sumerians used to observe the skies quite attentively. And when they started doing this, they would encounter some pretty weird stuff, right? And one of this very weird stuff is the so-called retrograde motion of Mars. So if you look at the night sky and if you keep very careful records of where Mars is located at each night, you will see something very strange. You will see that Mars is going from, let's say, left to right, and then something very strange happens. It pauses and it goes in the opposite direction for a while before again starting in its original direction and going like this. And if you are studying physics today, of course you know what's going on. It's basically the problem that you're watching Mars from a observation post which is rotating around the sun as Mars is also rotating around the sun. And so because you're watching at Mars from different positions, sometimes it's going to appear to go from left to right and sometimes from right to left. But to people who didn't have this concept, for them the Earth was a static reference frame. I mean, the Earth is basically standing still. This was mysterious. So how do you explain this? Don't underestimate human ingenuity. So Ptolemy came up with this idea. All right, so what I'm going to do is, instead of just having simple circles, I'm going to build epicycles within the cycles. So his idea was that, okay, so what's going on is that instead of going around like this, Mars actually does this spirograph-like motion. I don't know how many of you played with spirographs when you were a kid, but this was a very common toy when we were growing up. And so this would be like, you put a large circle and then you put a smaller circle within the circle. You put your pencil through a hole in the smaller circle. And as you basically, turn the circle with your pencil, you're going to trace out this cycloidal motion where you are going to have this circle within a circle type of motion, right? And so Ptolemy thought that he had explained Mars's retrograde motion as basically that Mars is rotating on a cycle which itself is traveling around a big circle around the Earth. Okay? And for a long time, this is something that was accepted as a perfectly plausible explanation. Until, of course, Copernicus came along and he realized that if you just change the reference frame, so instead of taking instead of taking Earth as the immovable center of the universe, if you say that the Earth is actually moving around the sun, which is kind of, the immovable center, you can explain the retrograde motion of Mars as simply an observational issue. Okay, so they are all rotating around the sun in circular motion, but because you're watching it also from a moving platform, it's like the point that you're watching from is also rotating, and something that you're looking at is also rotating around you. So you will sometimes see it going left to right, and sometimes you will see it going from right to left. Just as if you sit on a train which is sitting still, and a train goes past you, sometimes if you're not very careful, you might think that you are actually moving, right? Because it's all relative motion, right? Right. Okay, but things were still not very hunky-dory. Why? Well, people didn't realize that there was a problem until they started doing very accurate measurements. So as I said, the Sumerians had been watching the skies, 5,000 years before the birth of Christ, right? But just watching the skies is not enough. You need to do very accurate measurements. It has been said that science is born when people have the ability to do very accurate measurements. Okay, and we have this gentleman Tycho Brahe, who devised this, very accurate instrument. So this is, remember, pre-telescope. So Galileo essentially is credited with putting this glasses together, the curved lenses together, and in some sense making a telescope. So this is 50 years before that time. And so what he did was very similar to have you ever been to the Jaipur Jantar Mantar or the Delhi Jantar Mantar? This king of Jaipur actually put up observatories in 5 different places in India. And so this is something very similar to the kind of things you will see in the Jantar Mantar. Okay? So you basically have an arc like this on which marks are made in regular intervals, and you observe a particular heavenly body and to see which mark does its position coincide with, and then you basically record this. So you have a very accurate recording of where exactly on the night sky a particular heavenly body appeared on each night. And so therefore you can accurately track the position of each of the heavenly bodies night after night after night. Okay? And Tycho essentially filled up volume after volume with these observations. Okay? Enter Kepler. Okay? So Kepler wanted to use this data. However, remember, this is the 16th century. Okay? And scientists don't just share data. So what Kepler did was he had to become Tycho's assistant, essentially a glorified lackey, so that he could have access to this data. So when Tycho died, Kepler inherited all these measurements, and poring over these measurements, he tried to see, is there some way of digesting all of these volumes of data into some very simple relation where I actually don't need these volumes anymore. I can throw away the volume because I have this very simple relation between the position of this various heavenly bodies, so that you give me the date and I'll be able to tell, but just a simple calculation using my expressions, where in the night sky it would be seen. Okay. In some sense, data science is just that. It's a glorified mnemonic, right? It's an attempt by us that instead of trying to remember 1,000,000 facts about the universe, can we come up with some simple relations so that as and when we need it, we can actually recreate the data. Okay? We don't actually need to remember all that stuff. Okay? The first caveman effectively was doing this, right? I mean, there are so many possible dangers that this person can encounter. If you want to remember every single thing that happened to that person, okay, it's impossible. So what you do is you distill some abstract relations which signify danger, which signify sex, which signify food, the 3 basic needs of the person. And then using the simple relations, the person basically goes around his life. Okay? That reduces the cognitive load on the individual. So science is a way of reducing the cognitive load. Okay? So is making myths, actually. Okay? So you can trace a direct line from this human propensity to create myths and science. Okay? They're actually not all that very different, except that science relies on very accurate measurements so that you can make accurate predictions. Right? And so what Kepler did was he distilled the observations of Tycho into 3 laws of planetary motion, and now he could dispense with all of those volumes of data that Tycho had compiled, because he could, as and when, just reproduce all that data. And why did he need the accurate observations? So for example, Kepler showed that the planets go around the sun not in circular orbits but in elliptical orbits. And that's because from the records of Tycho, Kepler showed that there's an 8 arc-minute discrepancy if he assumed that the orbits were circular. And Tycho was so accurate that he just couldn't say that this was observational error. Okay? So the fact that there was an actual discrepancy means that he had to junk this cherished notion that planetary motion is circular. The Greeks believed that the circle is the perfect object. So that's why every astronomer who descended from the Greeks used to believe that the planetary motions are circular. So he had to junk this cherished notion and say, okay, I must accept that nature does not follow what we would consider beautiful, and they are actually elliptical orbits. Okay? So this is another hallmark of science, the ability to jettison cherished beliefs, because in the end your measurements actually don't agree with what you hope was true, right? And of course, then you come up eventually to a mechanistic model for explaining the observations. And very important, it's not enough just to explain in science. You also have to predict new unobserved phenomena, because that will give you a theory of the world. Okay? So what's the difference between Kepler and Newton? Kepler is not telling you why you have those laws. Kepler gives you no explanation why it's an ellipse. He just says that, look, based on the observations, an ellipse is the best explanation. It's Newton who tells you, using his laws of motion and a law of gravitation, why an ellipse is the way a planet is going to go around the sun. Okay? So using this simple set of axioms, just 3 laws of motion and a principle of gravitation, Newton could actually derive everything that Kepler had just phenomenologically written down from Tycho's data. Okay? And this is basically what we all strive for. Okay? A theory of the world, something that Tarun also mentioned. Okay? Right, so my view of physics as data science, therefore, boils down to doing accurate empirical observations. Okay, so this is what Tycho did. Infer general features of stylized facts. So this is what Kepler did. Okay, so you boil down all that empirical data into simple relations, and finally you do a model. This is what Newton did. But that's not enough. You now need to predict, and if your predictions don't match, you go back to the drawing board. Okay. So for example, when quantum mechanics came around, you suddenly realize that Newton was not enough, and you had to have new explanations, new models, right? And this is not very different from what data science is doing these days. The only difference is data science is dealing with millions of observables, possible observables, whereas physicists have by tradition been lucky in having to deal with only a few possible variables, right? And so data science circa 2026 is basically reduced to this, that you have a huge number of variables. So this is what I meant by the variable space. These are your outputs. So imagine that this is, did it rain yesterday and is it cloudy today? And the output is, what's the likelihood that it will rain? And by using lots and lots of observations, you are basically trying to build up some kind of a function which will tell you that given today's condition and yesterday's data, what's the probability that it will rain? Now, as the number of variables go up, this function building becomes even more complicated. And if you don't have human genius like Newton, what do? So we have to replace it with some automated algorithm. And the hope is that AI would be able to fill this gap. But just as Tarun said, let's not get too excited. So this is an advertisement from 1989. Okay. So we have been led to many false hopes along the way. So, maybe we should sometimes take it with a pinch of salt. All right. Right. So I'm really delayed. So but I can't help but tell you this. So another thing that physicists do is mess around with the maths. Okay. So there's this misleading notion goes about that physicists are very good with maths. Complete bosh. Okay. So what we do is this. So when the Trinity test happened, the first nuclear weapon test, Enrico Fermi, the famous physicist, dropped some scraps of paper from 6 feet above the ground, and by looking at how far they blew, so they blew over 2.5 meters, he estimated that the blast was equivalent to 10 kilotons of TNT. Okay. Now this is pretty close, even though it's just 40% of the modern estimate, because what he missed was the thermal and nuclear radiation, which actually don't contribute to the blast. So how did Fermi, without any fancy equipment, able to predict it so accurately? So he used a back of the envelope calculation. So this is something that physicists do all the time, and I would like to believe that you, as budding journalist will also be doing all the time, or you should be doing it all the time. Okay, it's a very, very useful trick. So these problems are sometimes called Fermi problems because Fermi loved to, challenge his students using questions like, how many piano tuners are there in Chicago? Okay. Now I understand that piano tuners is not something that you necessarily would be familiar with, nor will you be familiar with Chicago. So let's turn this into how many AC service people are there in Chennai? How would you approach this problem?
How many people use AC in Chennai first?
No, so, yeah.
Okay, and
How many households there are? What's the general population?
okay,
How many houses can a serviceman do in a day?
right.
Summer, winter.
Yep. Well, okay, summer winter is a bit more complication, but yeah. Okay, excellent, excellent. Okay, so the first step would be number of AC technicians that would find regular job is dependent on how many AC services are actually required in a year divided by how many ACs can be serviced by a technician in a year. Okay, so I need to estimate this and I need to estimate this. Inevitably I'll make errors in estimating this and estimating this, but hopefully the errors would kind of cancel out if I don't have a systematic bias. So let's start with the numerator. Okay, so how many AC service people in Chennai? The first step would be to calculate number of AC services in Chennai in a year. So let's say there are 8 million people in Chennai city, 2026. So this is, remember, within city limits. Wider Chennai metropolitan area is roughly twice the number. On average, 4 people in each household. 40% households in urban areas can afford ACs. And on average, a household has 2 AC units. And finally, each AC is serviced once per year, right? Now, important caveat, I'm not considering the fact that when the AC repair is so major that the AC has to be brought to the repair center. Okay, so you have to take all these caveats into account. All right, so if you just count this 8 divided by 4 into 40% into 2 will give you number of AC services in a year is about 1.6 billion, right? All right. Now, so AC technician requires 2 hours to travel and service an AC unit, right? And each AC technician works 8 hours a day. In reality, of course, technicians travel in pairs, so a senior guy with a trainee in tow, and they work 6 days a week, 50 weeks a year, and so therefore number of ACs serviced in a year is 1200, right? And so therefore, number of AC serviced people would be 1.6 million divided by 1,200, which is about 1,300, and this will be roughly double if you consider the Chennai metropolitan region instead of just the city. Okay, and you can try to, you can try to, measure this against or test this against actually what happens, sorry, what am I saying? Against the actual listing in directories and so on. And at least what this, 1,300 is not a number just to be taken very seriously, but at least it tells you it's not 13,000 or it's not 130. Okay, so you get an order of magnitude estimate. Okay, and this is something that physicists do all the time, and you should also do all the time as a sanity check. So if you just hear somebody say something, it's a very good ability to actually check, does this make sense? Okay. Something to do in your mind. Okay. So good. Chapter 3, rhythm of the walking gait. All right. So are you familiar with these pictures? Muybridge, pioneer of photography and also arguably the motion picture. So, do you know why he devised his instrument for capturing a horse in motion? No. Okay, you got all the other questions right, so, you are permitted one mistake. No. See, he was having a argument in a bar, like we usually do, and the argument was, when a horse is, running, is there any point of time when all its 4 legs are in the air? Right? Now, of course, when we argue, what will happen? We just have some more beer and forget all about it tomorrow. right? But Muybridge got really, hyped. And he said, let me figure out, is this true or not? Is there at any point the horse has all four hooves are in the air? Now, how do you capture a horse in motion? Remember, these are very early primitive cameras only. And so what he did was he set up a whole series of cameras. Each of these cameras have strings connected to the other side of the path. So as a horse gallops, it rips through all the strings, and so the camera shutters opens up and it captures the horse in mid-flight. Right? And by doing this, he basically showed that there is in fact one particular point at which all the four hooves are actually up in the air. Yeah? Okay? And he won the bet, right? Now, having done this with horse, he didn't stop. He said, hey, now that I have a setup which allows me to capture motion, so let me just see how, all kinds of humans, like for example, human walking gait. Now, how to figure out the human walking gait? So that's why I actually set this up. So you can actually think of it as a pendulum. Okay, so this looks like a leg, right, with the joint here. And so you can think of it as basically nothing other than a pendulum. Go back to Galileo, right? We use Galileo's idea, and we find that the time period, the period of our leg motion swing, is actually related by exactly the same formula as Galileo, right? Now, this actually gives us a fantastic relation with the speed. So what would be the speed? Speed is nothing but length by time. But we have already found that time is related to the square root of the length. And so it's L by square root of L, which is nothing but square root of L. And this gives us a fascinating glimpse as to what should be the walking speed of different animals. So for humans, the leg is about 80 centimeter. And we know that the average walking speed of human adults is 5 kilometer. And so therefore, if you look at an ostrich is roughly, its leg is double that of the human. And so therefore, its walking speed should be square root 2, about 1.4 times human. And we know that it's roughly 6 kilometer per hour, which is quite close. Penguins are roughly 4 times shorter than humans. So its speed should be half of that of humans. And lo and behold, it's actually less than 2.5 kilometer per hour. Okay, what about T-Rex? Give me one sleep. What about T-Rex? So the average running speed of humans is 10 kilometer per hour, and T-Rex is roughly, its leg is 4 times that of humans. So what is the running speed of T-Rex? Well, I'll just show you. What is the running speed of T-Rex? It's 4 times, right? So it should be twice the average running speed. So it's 20 kilometer per hour, which is in fact what paleontologists have shown, and which is something that Spielberg had conveniently ignored when he was watching Jurassic Park. So if you've seen the 93 Jurassic Park, that's Jeff Goldblum playing the role of a chaotician, you would see that the T-Rex is actually running close to the speed of a Jeep, right? And any paleontologist worth their name will tell you that if a T-Rex tried to run at that speed,
it's an impact tremor is what it is.
It had very serious
Fairly alarmed here.
risk of actually falling down and
we gotta get out of here.
fracturing its legs like I did, right? And so you have this, it's of course very dramatic when the T-Rex suddenly breaks cover and, there it is, and basically starts running after the Jeep, and the Jeep is basically going at 60 kilometers.
Must be faster.
Frog. Oh, okay. Interesting fact. So it's going at 60 kilometers per hour. I'm done. I'm just showing the clip. But it's just entertainment. Yeah. All right. And so basically, folks, just wanted to conclude by showing that a little bit of physics can actually give you a very good sanity check as to whether you should even take this seriously. All right. So I'm really sorry about going way over my time, but I have a way of doing this. And in fact, if you're taking my class, you know this gets to be a habit.
Think they'll have that on the tour?
Yeah.
Just to say, Yeah, okay. All right, guys. I just have to tell you, can you hear me? Yeah? Okay. So for the questions for Dr. Sitabhra Sinha, we will, once Dr. Srinivasan Ramani completes his part, which is equally fascinating because you talked about data, and he'll be talking about data science. And in fact, the topic is data journalism, approximation to the scientific method. So he'll be Dr. Ramani will be talking about this. So let me very briefly introduce you, and after his lecture, there'll be common questions, okay? For both Dr. Sinha and Dr. Ramani. All right.